the last area we have to discuss is really these changes to the respiratory system and muscular system in response to exercise. So again, we're looking at these acute responses. These are the ones that are pretty much immediate. Body hasn't had any chance to do any type of adaptation to this. This is just a stressor that the body is responding to in the immediate. Again, obviously during exercise, as well as after you're recovering, from bioenergetics we know that we need oxygen being delivered to the muscles as well as CO2 being taken away. And a lot of what we know from A&P is that CO2 is going to be a lot of times the determining factor in terms of how often you have to take a breath and therefore what your respiratory rate is going to be. So if you're looking at some of the stuff here, you can see that there's definitely going to be some different changes to the respiratory system. We're going to see really changes in rate, volume, overall ventilation, which is kind of volume per period of time, as well as changes in lung diffusion, as well as how much oxygen we're going to consume. The respiratory rate is going to go up, and I think everybody's kind of experienced this at one point or another. You start doing something active, very quickly you're going to see your breathing rate is going to go up. At rest, usually they say about 12 breaths a minute. As you begin to exercise, CO2 levels will increase because we're generating more CO2 by the breakdown of glucose to generate ATP. This is going to increase carbon dioxide as a waste product, which will end up in your blood being carried in a number of different ways, but it will act on your respiratory centers in your brain, and this is going to trigger you to start breathing faster. If we were to go out and run around the pond right now, out around Hawkins Pond, very quickly, if we did it one time, just kind of said run at a moderate rate, you would get done and you'd be breathing probably much faster than you were before you started out. The other thing that's going to change on this as well is we generally at rest are moving about 500 milliliters of air with each breath. I think what a lot of people will notice is if you start running, you're not only going to start breathing more often, but you tend to take deeper breaths. So instead of that 0.5 liters, you might be moving as much as 2.5 liters of air in and out of the lungs at any particular time. Again, moving more air means more oxygen getting down to the alveoli of the lungs, which means a higher pressure and more oxygen really being allowed to enter into the bloodstream. Those two factors together are really going to start affecting how much air you're moving in a particular period of time. So it's going to increase your ventilation. So ventilation is really, or that VE is minute ventilation, how much air you breathe in a minute, how much volume you're bringing in. Again, obviously dependent upon a number of things, how many breaths you're taking as well as how much you're taking with each breath. At rest, about 12 breaths a minute times half a liter of air per breath, that's about 6 liters per minute of air being ventilated in and out of the lungs. What we're going to see is there's definitely going to be a change in this as exercise increases. It's quite a linear relationship to that oxygen consumption early on here. So the ventilation to the amount of oxygen consumed at up to about 55% of max, you're bringing in about 25 times more volume than the amount of oxygen you're consuming. But we're going to see definitely an increase in ventilation, the amount, and you can kind of see it on here, just overall the amount of liters as really exercise increases. What we generally see when we look at changes in ventilation rate, it kind of gets subdivided into a number of phases. You have phase one, which is pretty much right as you start exercise, you're going to see a pretty sudden increase in ventilation, breathing rate as well as breathing volumes, and therefore that overall ventilation. We're going to see then it gets into the second stage where it's going to gradually increase above that sudden onset level to start getting to, as long as you're kind of doing a steady state of activity, to getting to a pretty much a plateau phase where you're maintaining this level of ventilation. It's applying enough oxygen to the muscles and that ventilation level is maintained. What we're going to see is after you end exercise, we're going to see a slightly higher than resting period type of ventilation as we're really kind of putting this stuff back. And it's that post-exercise increase in ventilation is that epoch. It's just really what you're doing on this one. That's that oxygen debt that we learned about in AMP2, where a lot of the things like putting back the creatine phosphate, putting back anything on myoglobin oxygen stores, building back up ATP stores that are in the muscle, all this stuff is going to use excess oxygen in the post-exercise level to get the muscles generally as quick as the body can back to a pre-exercise state. And that's really why we see that gradual decrease and not a sudden decrease back to pre-exercise levels. So if we start looking at the ratios of carbon dioxide, that ventilatory equivalent of carbon dioxide relative here, we're going to see this is pretty linear with levels until we start getting quite high up in terms of output. So the minute ventilation relative to carbon dioxide produced is pretty constant during steady state exercises. It's a very, for the most part, very linear relationship until we start getting into a little bit more of an extreme exertion. And as we get from that moderate level, that steady state level, so if you're going out and running, let's say, and an easy run for you is 830s, you would see a pretty linear relationship between the ventilation and the carbon dioxide generation. Really what will start happening as we get to more and more strenuous levels, we start actually ventilating at a much higher rate than the amount of oxygen we're actually taking in and consuming. So that it's a disproportionate increase in ventilation relative to the amount of oxygen we're delivering to the muscles. The point at which this happens, where you start getting this big increase, is what we refer to as the ventilatory threshold, or VT. You can see right here we're having a pretty linear relationship in terms of that and oxygen consumption. At the ventilatory threshold, we start seeing this steepened curve here where the ventilation goes up, but the oxygen consumption is not increasing quite as much. We get a much steeper curve at this point. And you can see, then again, there's another break point again as that blood lactate levels start to really climb. In these non-steady state ones, what's really going on here? Again, it goes back to our breathing regulation and why we breathe when we do. Breathing rate is really a function most often of carbon dioxide levels in the blood and acidity of the blood. Both increasing acidity of the blood and increasing carbon dioxide levels, generally because they go hand in hand, as we learned in AMP2, are going to both be a thing to stimulate the body to breathe more often. One of the things that happens is we start going anaerobic and start using glycolysis more in terms of increasing muscle work. When we go anaerobic, we're going to generate that lactate, becomes lactic acid. It's going to get out into the bloodstream and interact with that bicarbonate. One of the byproducts of this is this lactate combining with this is we're going to generate more CO2 in the blood. We generate more CO2 in the blood. That is going to trigger us to breathe more often. So what we have going on here now is it's not muscle metabolism that's generating this CO2. It's the fact that we went anaerobic is increasing CO2 levels in the blood above oxygen consumption levels. And this is going to start triggering an increased breathing rate that is no longer linear to oxygen consumption. So that non-metabolic from the breakdown of glucose or whatever else is going to start stimulating this increased ventilation, that CO2 from that. And this would be true of other things as well. If you're doing a keto diet, for example, you're going to have a higher breathing rate because you're getting those acids from the ketosis, and it is going to actually increase the amount of acidity and CO2 in your blood, and you'll start breathing more often. CO2, like I said, is generally a byproduct of the Krebs cycle, or the TCA cycle, whatever you want to call that one. It's usually generated there. But again, as we start getting this from that lactate and lactic acid in the blood, you can see this breathing rate starts climbing in a nonlinear fashion. So again, driving that buildup of lactic acid in the bloodstream is driving this increase in ventilation well above oxygen consumption. So again, we get this disproportionate one here. And again, that is referred to as that, where it breaks with that linear relationship, is that ventilatory threshold. One of the things that's also interesting with this one, and we've talked about this a little bit with lactic acid and lactic acid buildup, a lot of times that point of that VT is actually going to correspond very nicely with the onset of the buildup of lactate in the bloodstream. So generally we're going to see, you can see on this graph right here, here's VT. Here is that point of lactic acid buildup where it starts getting more than we're clearing. And you can see those break points kind of correspond with one another. It is a way to non-invasively test for that. It's one of the things you can look for is that increase in ventilation rate that is very much higher than what you were doing in a steady state activity, is a way to look for that without actually having to test for lactic acid in the bloodstream. Again, it is an estimate when you're doing that though, so a lot of variables go into CO2 production, blood pH, bicarbonate levels, respiratory exchange ratio, which we've all talked about. They're all related to that onset of blood lactic acid. But like I said, looking for that VT is a way to kind of do that, but it's not going to be a begin all end all. The only way to really measure the onset of blood lactic acid levels is to actually measure it in the bloodstream. Like I said, that change in the VT, that ventilation, that VT break, it is a good estimate of where it probably is, but again, the only way to actually for sure measure this is to know this is to actually measure that in the bloodstream. Like I said, a lot of times they try to do this bloodless where we look for that break point and see if we can do that one, and we can use that as a kind of an idea or a pace at which we start going anaerobic. It's a good estimate, but again, not an actual measure. So, ventilation limit for aerobic capacity. Does ventilation limit this for an average person? So what we're really kind of getting at here is the ventilation limiting factor a lot of times for an average person. So like it says here, if inadequate breathing capacity, limited aerobic capacity, ventilatory equivalent for oxygen would decrease. What actually happens, healthy people tend to overbreathe relative to the VO2. So it's really generally not the limit. It's not the limiting factor generally. Another thing that becomes important on this one too is also breathing does require energy. So we need a couple of different things to be working well in order for this increased ventilation to be effective at all. And one of those is that the lungs need to be able to expand very easily, so that's that compliance, as well as we need our airways to be open very well. And as I was already saying, as we start breathing more often, we start taking deeper breaths, the amount of energy that costs us becomes important as well. And as we get into higher and higher levels of exercise, so like I said there, at about 100 liters per minute of ventilation, how much it's costing us about 20% of our VO2 to just do that level of breathing. So as we get higher and higher levels of ventilation, the respiratory component or respiratory cost of the muscles for breathing starts to become higher and higher. And this is just kind of showing you these different levels of exercise and the basics in terms of that amount of ventilation. You can see at these very heavy ones here, we are getting up to 120 liters per minute relative to when you were doing about 6 liters per minute under no exercise. So you can see we are capable of generating quite a large amount of air movement with the lungs. The other thing that tends to happen with the respiratory system is when we get into these strenuous exercises, we do tend to see an increase in diffusion. Again, this is partly to dilation of the capillaries and increased blood flow to the lungs. We can see a bigger movement of oxygen in here. We also are pushing a lot more CO2 out from the blood into the alveoli where it's breathed out. So we are getting a bigger movement, about a threefold increase in oxygen and CO2 diffusion as we increase these levels of ventilation, as well as dilating the blood vessels, increase blood flow to these areas. So really the last thing to look at here is going to be these muscular responses to acute exercise. To kind of do it in a real quick way here, we are having, as we increase levels of exercise, we are recruiting more muscles, which is going to lead to an increased rate of ATP production. We are going to increase our use of fuel and therefore increase ATP production. As the muscles work, we are going to be generating heat. We're going to have to then start regulating that heat by generating increased blood flow to the skin to regulate that temperature. And we've already talked a little bit about here, but with the muscles, they are going to a lot of times be releasing local factors that are going to increase that oxygen extraction from the bloodstream, which is going to generate a bigger arterial venous difference in oxygen levels, which allows us to increase ATP production through aerobic means. And again, one of the things we'll see as we start getting into overall chronic response to this is we're going to start trying to generate ways that we can get this to become more and more efficient, that release of oxygen from the bloodstream. The other thing we're going to see is we do have different fiber types in the muscle. So depending on the level of exercise and the duration, certain fibers are going to be more efficient than others. So we have type 1 and type 2 fibers, as well as kind of the intermediate fibers, which kind of the type 1, type 2A, and type 2B. So type 1 fibers are much more aerobic fibers. They're generally referred to as slow twitch a lot of the time. Much more able to use oxygen and do it for a much longer period of time. These are firing at a lot slower rates than the type 2 fibers. Their ATPases are slower. They don't tend to turn through that oxygen, the ATP, quite as fast. Generally good for endurance and other things like that, long-term running, swimming, cycling, like it says there. Where your type 2 fibers, they are much more powerful generally. Can contract at a much faster rate and with a lot more power. Good for speed and power events, but again, not going to make efficient use of ATP. So again, depending on what type of activity you're doing, you may be triggering one of these fibers to be more active than others, where you can see sprinters are mainly type 2, not much of type 1 there, where you get these more endurance events. You can see it's a lot more type 1, those slow twitch fibers, and a lot less of the fast twitch. And again, just a good summary of all this here, looking at the respiratory system, increased volumes, increased rates, overall increases in ventilation. When response to exercise, cardiovascular system, increased output due to both increases in the heart rate and stroke volume. We see an increase in that systolic pressure, a larger arterial venous difference, redistribution of blood flow to those areas that are active in the muscular system. We increase the muscle fibers being recruited, increase the metabolism. We consume more oxygen at these ones. We're going to increase byproducts that a lot of times are going to increase the drop-off of that oxygen, and the same thing with the temperature. It's going to increase the drop-off of the oxygen at those ones here. All these things letting the body respond to this exercise stressor in that immediate short-term time.